There we go. So this is me. I'm director of community at a company called Mesa. Mesa build cluster orchestration software. We work around historically around Apache Mesos, but also now around Kubernetes. And we have two big engineering offices, one in San Francisco and one in Hamburg. Just to start by setting the scene a little bit about what we're going to be looking at today. So Kubernetes and most orchestration systems built around the idea of declarative state work very well for stateless applications. And a stateless application, for those of you who aren't familiar with this space, is a program that doesn't save any client data generated in one session to use in the next session with that client. Each session's carried out as if it was the first time, and responses aren't dependent on data from the previous session. So what that means in practice is that we can start and stop these stateless applications, and when we start them, they'll just start up and start executing. And in general, we'd run this kind of application behind a load balancer, and we can scale these stateless apps up and down by adding or removing instances. And we can also deploy new versions of them very easily by basically just replacing all of the running instances. And we can have various ordering strategies for performing those tasks, blue-green deployments, for example, for testing new versions. But fundamentally, the management of them is kind of binary. They're either running or they're not. And stateless applications are kind of intrinsically intertwined with the move towards microservices architectures, where we connect together many very simple applications where each have a very well-bounded function. And also to the adoption of container technologies to manage them, because they're fundamentally well-suited to those patterns that systems like Kubernetes give us. So we simply declare that we want a specific number of an application to exist, and Kubernetes will create them for us. And again, it's kind of binary, you know, they're either running or they're not. We don't have to worry about any complex operations to configure them before we start deploying. So if all applications were stateless, then the world of application deployment would be super simple. And you'd be forgiven for thinking, if you read the tech press, that that's the case everywhere in the era of microservices. But unfortunately, that's not actually true. The second class of applications that we deal with are stateful. And here the app is retaining data or state across its entire life cycle. And you know, older, more monolithic applications like SQL databases fit into this paradigm. But there are also many architectures where the individual elements making up a particular service are clustered together in some way. They're sharing some kind of data between them. And typically, these kinds of applications have a set of lifecycle states which require logical ordering of actions in order to maintain operation. In general, we can't just start and stop things and expect the overall service to continue to operate or continue to be performant. And we might need to wait for data to rebalance. There might be multiple steps involved in an upgrade process. And that applies not only to upgrading, but to scaling, to failure scenarios. And all these operational strategies require domain-specific knowledge to manage them. So they're kind of unique to the application. Those operations for a Cassandra cluster are different from what they might be for a Kafka cluster or for an HDFS deployment. And Kubernetes was originally very focused on the stateless application architecture, as I said earlier. And one of the fundamental features of Kubernetes is that the scheduler can move pods around between agents. And this works fine for stateless applications, but not so well for stateful, which tend to like their storage and their network not to change during operation, unless we handle that in a very specific operational way. So in order to try and handle the complexities of stateful applications, Kubernetes added this concept of stateful sets, which adds the idea of stable network and storage. But this doesn't really solve all of our problems, because Kubernetes still fundamentally doesn't know what's happening inside the pods. And so as an example of this, we can consider a rolling upgrade of nodes in a Kubernetes cluster. And let's imagine we have a replicated master-slave database of some description running in a stateful set. The node running the master upgrades and reboots, so we may lose some transactions at that point. And at this point, our imaginary database cluster may trigger a re-election and elect a new master. So when the original master pod is rescheduled, it comes back up and into a cluster with a new master, which it may be unaware of, and that might cause issues in itself. But even if it then settles back into its role as a slave, Kubernetes sees all the nodes are running again and starts to roll out an upgrade to another node, which may well hit our new master, and so on. So how happy is this database likely to be during this process? And the point here is that the domain knowledge of how to safely do a rolling upgrade when you've got things like database clusters running isn't captured by that concept of stateful sets. So how do we automate and package that knowledge up? So the emerging solution to that problem is the operator pattern. And operators basically encapsulate operational tasks in code, and that code can be run either when an API is invoked, it can be run automatically, it can be run on a schedule. So we can orchestrate application lifestyle actions using the Kubernetes APIs. So fundamentally, they encode all that domain-specific knowledge about the lifecycle actions required for the application. How do I scale it? How do I upgrade it? How do I deal with failure scenarios? And they achieve all of this using native Kubernetes APIs. So what are operators? Well, when we install an operator, we generally get the operator itself, which is the kind of code that manages the lifecycle of that particular thing, and that's where all that domain-specific knowledge is encapsulated. And we'll also likely get a bunch of custom resource definitions, CRDs. And custom resource definitions extend the Kubernetes API to add new resource types. So once we've got that type, we can put some data into it, give it to Kubernetes, and Kubernetes can then instantiate an instance of it. In this example here, we're looking at some code to instantiate a MySQL cluster. But the important thing here is that each of these operators is unique. It's purpose-built for each specific application. And up until now, there have been two main ways of building operators. The first is the operator framework. This originated at CoreOS and then came into Red Hat when CoreOS were acquired. It's mainly developed by Red Hat and IBM. And you can build operators just using Ansible and Helm charts, but there's also a Go SDK. When you want to encapsulate complex lifecycle actions with Ansible or Helm, generally those operators will have some limitations in their functionality because of the underlying technology that's been used to build them. So most complex operators are built using the Go SDK. And then there's the KubeBuilder project that's part of the API machinery SIG in the Kubernetes project. And that's focused really on extending the Kubernetes API. Again, you need to write a lot of Go to build using this, and there are some gaps in the lifecycle coverage for operators done in that way. But the point is that building operators can be really complex, and it requires a lot of knowledge about how Kubernetes works internally. It also requires very deep Go expertise, as well as all that domain-specific knowledge about the particular application you're going to write an operator for. So for a lot of organizations who are looking to do orchestration in this way using operators, you might well have to bring in substantial engineering resource in order to actually build one yourself. And I guess that the kinds of tasks that you're going to want to automate are also fairly variable. You know, automating, adding a replica to a database cluster is pretty straightforward, but how do you fix things like a write-ahead log or something like that? So the engineering effort that goes into making really high-quality ones is pretty considerable. As an example of this, one of the major NoSQL vendors has built an extremely comprehensive operator, and it's about 40,000 lines of Go, and it took over 1 man-year of effort to build this thing. So, you know, you can see that's a very big investment for anybody to make, even for a software vendor to make. And even something like the etcd operator, you know, etcd's got a fairly simple life cycle, and that's around 9,000 lines of code. So, historically at Mesosphere, we've worked in the field of Apache Mesos, and the story in Mesos around stateful applications is slightly different. This is what the architecture of a Mesos cluster looks like. We have a bunch of agents that are running on your infrastructure at the bottom. We have a number of masters, only one of which is in control at any one time. We have a zookeeper cluster that's managing leader election for if my master fails. And then we have what's called frameworks running on the top of these. And so what makes Mesos different in one sense from Kubernetes is this idea of two-level scheduling, that the Mesos masters themselves are really only concerned with resource allocation. So they're offering up resources to the frameworks. The frameworks then decide whether they want to accept or decline that particular piece of resource that's been offered up from the cluster. And the frameworks consist of a scheduler, which is the bit that's running at the top, and then an executor that actually is the thing that launches workloads. But the key thing here is that that application logic, that domain-specific application logic, in Mesos has always been encoded in the scheduler, separating out those two concerns. And so that scheduler model is known as non-monolithic. The Mesos master doesn't need to know about all of the things, it just needs to know about what resources are being offered up from below. And the application-specific knowledge is held in the application scheduler. So that means that those application schedulers have always been able to handle complex lifecycle actions for stateful workloads. But Mesos frameworks are also incredibly hard to write. They require, in exactly the same way as Kubernetes operators, they require very deep knowledge of the internals of Mesos, how to achieve specific things. So at Mesosphere, we spent a lot of time looking at how to simplify that process to allow developers to more easily build Mesos frameworks. And it occurred to us after looking at lots of scheduler implementations that there was actually quite a lot of commonality between the types of actions that are encapsulated into schedulers to manage application lifecycle. And so that led to the creation of the DTS Commons SDK, which provided a layer of abstraction for developing frameworks, and basically allows you to define a framework mostly in YAML. And one of the core concepts within the SDK is the idea of plans that are basically sequences of events which define a particular lifecycle event. So a lot of plans are, you know, you can consider the structure of them to be fairly generic. For example, deployment, you know, there's always going to be a deployment plan. There's always going to be an upgrade plan. And so those are defined in the SDK to remove the necessity for everybody to re-implement that every time they wrote a framework. So when we start to look at the operator landscape, it seemed like this was a pretty familiar problem space. We saw developers having to implement the same steps, a lot of complexity being expressed in a number of lines of code and in engineering time to implement. So we took what we learned from that DTS Commons SDK and created the Kudo project with the aim of simplifying operator development. So Kudo's an acronym for the Kubernetes Universal Declarative Operator. And so rather than implementing a custom operator for each application, Kudo provides a universal operator with this concept of plans built into it. So it allows operator developers to define a lot of the code in YAML. It started out as being built on top of KubeBuilder. It's a fully open source project. So you can also think of it as a kind of a way of simplifying KubeBuilder-based development. And you know, it's in the early stages, but we're actively working to build community around this, and hoping to push it into a CNCF sandbox project. So in comparison to the other ways of building operators, Kudo can create complete operators without needing either particularly deep knowledge of Kubernetes or writing any code. Just by defining those lifecycle phases and actions in YAML, we can orchestrate those lifecycle stages using the built-in custom resource definitions which Kudo supplies. And Kudo's ultimately just Kubernetes. There's no DSL to learn, there's no proprietary APIs, there's no external data store. It's just Kubernetes APIs. So as a result, it's a lot easier to learn, and it supports all the native Kubernetes tooling, things like Kustomize for merging YAML together, kubectl, you know, it's all just managed in the same way as you manage any other things within your Kubernetes clusters. And it maps to the same resource model that you're used to using with other Kubernetes resources. So there's a few core concepts that we need to understand when we talk about what Kudo is. Firstly, a framework. So this is the kind of high-level description of a deployable service. It's represented as a custom resource definition object, a CRD. And we can see an example here of the Kafka operator. And then we have this idea of framework version, and that represents the particular implementation of a framework. So it's possible to have installed multiple framework versions of a particular framework. You may want to pick and choose between different versions of a particular piece of software. And this is really where all of the smarts are defined. And the purpose of the framework version is really to give Kudo the details that it needs to become an operator for that particular application. So as the operator will execute a plan to establish all the instances of the Kafka components in the cluster as we ask for them. And you know, in this example here, we'll look at some code a little bit later on. But you can see there that we're going to make sure there's 3 brokers for each instance, and we're defining which version of Kafka we want, and we have some parameters and stuff like that. And then in terms of plans here, we have just a single deployment plan. And then finally, nested into all of that is this instance CRD, and the instance is the actual thing itself. So it's a CRD to represent a particular application instantiation of a framework version. So plans are how Kudo frameworks convey progress through particular service management operations like deployment, like scaling. And a plan is kind of got this 3-step hierarchy. A plan is comprised of phases, and then phases are comprised of steps. And we kind of collectively refer to all this stuff as elements. And the status of the execution of a particular plan is captured through another CRD, a plan execution CRD. And the phases of the plan determine what their status is based on the steps that they've executed, and then the overall plan status is defined by the status of the phases, and then that's captured in that plan execution CRD. And we'll see that a little bit later, I think. And then we have this concept of deployment strategy, and this is about which the way in which a particular plan or step is executed. And by default, these can kind of be serial or parallel. So, you know, obviously what that says is either I can execute all of those steps at the same time, or I have to wait for steps to complete before I start trying to execute the next one. And a trigger is what happens when a parameter is updated in an instance object. It's part of the framework version, and it gives you just more customization for what actions you want to happen. In this case, we're looking over here at the trigger for the change to a backup file, and the trigger is going to trigger a backup step, which is going to redo that particular backup task. So if we have a closer look at what the YAML looks like, hopefully everybody can see that. Here's an example of framework version. And you know, as I said earlier, this is really where the magic happens for a particular version of a framework. So we could see the plans for the lifecycle phases that are being defined here. For the deploy plan, the strategy is serial, so each of those tasks is going to be executed serially. And we can see in this example, we've got a couple of other plans. We've got a backup plan and we've got a restore plan. And it's also worth noting here that tasks are defined outside of this YAML, this particular YAML hierarchy, so you can reuse them across different plans. And here's an example of a set of tasks defining what the resources, which YAML applies to each of those tasks. Although the patches section we haven't yet implemented, but that's going to be on the roadmap that you can kind of munge YAML together for a particular, maybe adding custom configuration for your environment, and then you get those things executed at the same time. And that will kind of let you separate out site-specific, organization-specific configuration from perhaps a default upstream configuration for a particular framework. And then in the framework version, we also define configuration information about the application itself. In this example here, we've got some parameters. We give a parameter, we can give it a default value. Those can then be overridden at the instance level when we define the particular instantiation of that application. And you can see that we can refer to these to the parameters that we defined further on in our spec using templating. This is Moustache templating. And here's an example of an instance. We can see we're referencing which framework version we want to use. So as I said before, you could have multiple framework versions of a particular framework installed in your cluster and decide when you instantiate an application which one you want to use. And we're defining some parameters that we're going to override from our framework version. Kudo also includes a CLI extension to kubectl, which allows us to run Kudo-specific commands natively inside kubectl. So we can look at the excuse me, at the status of particular plan executions. We can actually install frameworks directly from the Kudo upstream GitHub repositories. Again, this is in very active development, so things are being added to this all the time. So we're going to look at some actual Kudo operators in a minute, but I wanted to share a couple of things that are likely to be coming in the next versions of Kudo. Firstly, we have this concept of dynamic CRDs. So the idea here is that CRDs can be added to a particular framework on the fly via another known set of Kudo CRDs. So the controller doesn't need to know when you install that framework about every single action that that particular framework is going to do. So it might be as an operator, you know, as an operator who's a person operating a cluster, you want to change how a particular plan is executed, or you want to change ordering or add entirely new sets of actions. and you may want to change what things trigger which thing, and you'll be able to do that through dynamic CRDs. And what that kind of means is a slight change to how it's structured at the minute, in that operations themselves move up to become a first-class object, a kind, and that effectively means you can trigger operational actions just by instantiating a particular object into the cluster. And we're also doing some work around the concept of framework extensions. And so because the frameworks themselves are just defined in YAML, we can add functionality to a framework and have extensions to that framework maintained separately and then merged together at runtime. So some examples of that may be platform-specific extensions to a particular framework, or then proprietary internal extensions that are maintained separately within an organization or tied to a specific user. And one of the problems we'd also like to improve on, and this is not unique to Kudo in any way, it's a kind of a problem space for Kubernetes generally as Kubernetes gets more and more complicated, is that YAML is fairly terrible to work with. You know, especially when you start creating complex objects. For complex operators built using YAML, you could clearly end up with a lot of YAML there, and it rapidly becomes pretty unreadable. And Kudo uses Kustomize, which is another Kubernetes project, under the hood to patch in and template YAML. So we're kind of exposed to some of the problems that exist in Kustomize itself. You know, merge strategies can be quite complicated, and mustache templating on top of Kustomize can also be fairly confusing. Kustomize was originally built as a CLI tool, so it doesn't quite map into the paradigm that Kudo is trying to do to use it inside an application. And so one of the emerging solutions to all this YAML in Kubernetes is Q. Q stands for Configure, Unify, Execute. It's a project that originated at Google, and it's basically a kind of JSON superset that was influenced by their internal configuration language for Borg, which is the internal container orchestrator that Google use. And in practice, it ends up looking a bit more like a DSL than YAML. And using Q, we should be able to get to this kind of thing where we can define an operator much more simply, and it looks a lot like nested JSON. When I look at this stuff, this reminds me a lot of Puppet. So you know, I think it's a lot easier to look at that kind of code than it is to look at massive sheets of YAML. And so here's a more complete example. You probably can't read that from there, but you know, basically that kind of that would be 2 or 3 times as long if we had to define it all in YAML. So here's the exciting bit. Let's see whether this works. Just give me 2 seconds to just switch this around. Oh, let's get out of that. Here. Let's see whether the demo gods are shining on us today. All right, mirror. Okay, it's looking quite good. Let's move that. Okay, how's that text size for everyone? Shall we see whether we can make that a bit bigger? Right, so here I've got Minikube running on my laptop. It shouldn't have anything running in it. It's completely empty, and we can see if we look at frameworks that Kubernetes right now just doesn't have a clue what a framework is. So the first thing we need to do is to install our framework CRDs, our Kudo CRDs, which will effectively instantiate those things within the Kubernetes cluster. And so here, you know, those are the 4 things that we talked about, plan executions, instances, frameworks, and framework versions. And so, and then we also want to run our operator. I'm just running this locally from my local GitHub checkout. But at this point, now if I run my get frameworks again, so now Kubernetes knows that a thing like a framework actually exists. So at this point, we can start to actually do some stuff. We're going to just install a Zookeeper cluster to start with, and you know, if we look at the YAML for this, so that's the framework.yaml. Again, it's super simple. Just says basically that this applies to the Kudo API, and so we can just do kubectl apply. And now we know that we've got a Zookeeper framework installed. And if we look at our version.yaml, this is obviously a lot more stuff in here. So we've got a bunch of parameters that are defined that we can then use later, and we can use them when we define an instance. We're setting out what our templates are here. So we've got our services.yaml, we've got our pod disruption budget YAML, and we've got our stateful set, which is going to give us our Zookeeper cluster. And then down here is where we start to get into the Kudo specific stuff. So we're defining for each of our tasks that we're going to want to run, which of those YAML files are going to be used to handle that task. And then right at the bottom here, we've got what our plans are. So here we can see our deploy plan. It's got a serial strategy, but it's only got a single phase there anyway. But the phase can actually be implemented in parallel, and then we have a validation plan as well. Right, so install that one, and then when we want an actual Zookeeper cluster, we're going to use this Zookeeper instance.yaml. And you can see we're just overriding there the number of the Zookeeper CPU setting. And so hopefully, if we now and so we can see there that what's happening is that Kubernetes is now deploying those Zookeeper pods. That's going to build us a Zookeeper cluster. Just give that a second. Hopefully got internet. Yeah, here we go. Okay. Let's just move that up a little bit. So we can see we've now got an instance of our particular Zookeeper framework. And we're now going to install a Kafka cluster as well. Kafka obviously relies on Zookeeper. So we can see Kubernetes now knows about our Kafka framework. And it's now starting to deploy, hopefully, a 3-node, 3-broker Kafka cluster. I think my internet connection is a bit slow here. Right, let's come back to that one in a second. So the other example that I've got here is for a MySQL framework. And this MySQL framework has some slightly more complicated plans for both backup and restore. And so we can start up MySQL, we can take a backup using the Kubernetes APIs and then restore that backup back into that particular MySQL instance. Let's see whether, hopefully I've got enough CPU and RAM in my Minikube to deploy all this at the same time. So we can see there that's deployed the framework version and instance all together in a single YAML file. We can see our Kafka clusters now up and running. And we're just waiting for our MySQL now. Okay, so that's all up and running now. So at this point, I want to use my cheat sheet for this because I've got some variables that I need to set. So I'm just going to set an envar there to make it easy. And in that MySQL deployment, we've just got a single table, this example table. And we're just going to stick some data in there. Right, so there we can see we've got 3 rows in that table. So now we're going to take a backup of that, and I've got another YAML here that's just a plan execution, and that's just going to execute the backup plan for that MySQL framework. And we can see that starting to run. And now that's completed. So they've just deleted all of the stuff from that particular table. So we can see it's completely empty. And now I've got a similar plan execution YAML for the restore. So we'll just apply that. And that's already happened. And now if we do that, we should see the data back there again. Okay. So let's just So we'd really like other people to get involved in Kudo. If any of this has been interesting, there's a whole bunch of community resources. We have the Kudo website at kudo.dev. And you can see the code on GitHub. We also have the #Kudo channel on the Kubernetes Slack, and there is a mailing list. And we also have a weekly community meeting, which is held on Zoom. All the details for that are on the Kudo website. So thank you very much for listening. I'm happy to answer any questions.
Okay, thank you again, Matt. I really liked the naming of your MacBook, I have to admit. Okay, are there any questions in the audience? None so far I can see. Well, I guess thanks, Matt.
Thank you.
We will see you at the evening event?
Yeah, hopefully, yeah.
Okay, exactly. Nice.
Thanks, folks.
Okay, thank you again.